I wanted to take a minute just to introduce the ideal gas law. This is something that I think you've probably worked with before in chemistry class. But a little refresher can't hurt, and this is something that we'll be using extensively in our study of gases. So the ideal gas law, in one format anyway, is written as PV equals nRT, with meanings as shown here. So this is a relationship that's been determined experimentally. You can also calculate this analytically through a variety of, really complex calculations that we aren't going to get into at this level. So, for this class, you can just take my word for it, I suppose, or at least accept that the AP testing folks they'll accept this equation. So we've got pressure. Pressure for this equation is going to be measured in pascals or newtons per square meter. Actually, all of these except for the R value, the units that we use for that will depend on what number we're using for R. So there are a variety of different values of R that we can use, each with different units here. R in this equation serves essentially as a conversion factor. So if we had different units, we could just have a different number for R and different units there. The version that's given to you on the equation sheet for the AP's test, though, is joules per mole Kelvin. So that means that that sets all of our other values or all of our other units. So pressure needs to be in pascals, which is the same as newtons per square meter. Volume needs to be in cubic meters. Now this one is an important one to note because we're typically not going to be given cubic meters. That's not a real common unit for volume. So we will have some conversions that go in that frequently. N is going to be the amount of gas in moles. Remember, moles works just like the term dozen does. So you could have 2 dozen eggs. That's 2 packs of 24 eggs. Well, a mole is like a pack of atoms, except it's way more than 12. It's 6.02 times 10 to the 23rd eggs or atoms or molecules or anything else. Then we've got this universal gas constant, the conversion factor, and then the temperature. And be careful that you use Kelvin for that temperature. That is important. It has to be the absolute temperature. So we keep referring back to this ideal gas law for calculations involving expansion and contraction of gases. And we'll come back to it a little later on when we talk about work and heat and how gases do work on systems and things like engines. So this is definitely a big part of the rest of what we're doing with fluid mechanics.